In the last tutorial, you saw how you can filter the points, so you can control where do you spawn your objects in your level better. And now let's see how you can modify the attributes to achieve better control over the spawning of your objects and the properties that they have. Let's continue our journey into PCG mastering with understanding the attributes and how to modify them. And this is maybe the single biggest strength that you can have in complex PCG graphs. Let's use an example similar to the previous session with this floor of a room covered with toys objects. So let's see our current PCG graph. Get landscape data node, surface sampler, which is sampling the landscape, and then we have these transform points, which we'll look at it right now, what it can do and how does it achieve these results. So let's zero out everything to have the default result of the sampling and the static mesh spawner from our previous video, which is selecting a random toy and placing it into our world. So let's inspect the surface sampler by right-clicking and clicking inspect or clicking the A key while you have it selected. And this will show you all the points that it's sampling from our landscape and all of the attributes that they have by default. And again, the default attributes have this dollar sign in the beginning, and all the other attributes which you add will not have such special symbols. So this is how you can differentiate the default ones by the custom ones. So first let's start by seeing how we can modify the default values and what all the default values do. So we'll start by using these transform points. So let's connect back the surface sampler to a static mesh spawner. This is just the simpler graph with just 3 nodes, and you can drag and add transform points. And I'll disconnect the static mesh spawner. And by the way, I'm doing this by holding the Alt key and clicking here on the connection, and this will disconnect it. And now if I drag out from this out pin to this in pin, it will connect them. So you'll see there's no difference when we add these transform points with the default values. The way that the transform points works is it will assign a random value to a given attribute based on the minimum and maximum values that you enter here. For example, for the offset of the position, which is these two first inputs, you can enter a minimum value and a maximum value for each axis, and the axis always in Unreal Engine start with X, then Y, then Z. So the Z axis is the vertical axis, and you'll see that if I enter here 10, for example, we'll have a random vertical offset between 0 units and 10 units. So some of the toys will be on the ground with 0 offset, some will be with 10 units offset up in the air, and you will have all in between values, just a random value assigned to each object. And if I want the minimum to be below the floor, for example, I can put -10 here, and you can see that some of the objects will go into the ground, some will go up from the ground, and it will be randomly assigned a value here. And if we inspect instead of the surface sampler, which, as you can see here, the position Z for all the points is 0, but if I inspect now the transform points by clicking A key to the transform points node, now you can see this random value being assigned. And this is very important to understand. We have this type of nodes that are created to do something with our default values, but we can modify any value in this way with custom calculations and custom random values. Later I'll show you how. But the most important thing to understand here is that this thing is just assigning a random value to the position based on this criteria that you enter here. So if I put offset of 0, minimum offset of 0 and maximum of 10, if you click this column to sort by this value, you can see that the value is between 0 and 10. And this is all this column does. It's the control of how much you have the minimum and the maximum of this random value. And of course, you can do the same for the other axis. So let's put again 0 to the z-axis because we don't want floating objects on the ground. And let's put some random offset. X will be minus 50 and in Y again minus 50 and the maximum will be 50. And this will move each point 50 units to the left and right and front and back. Random amount between minus 50 and 50. So in total 100 units can be the random area for each toy. And we will not have any randomization into the z-axis. So we'll change the position x and position y based on random amount between these values, minus 50 and 50. If I put, for example, 0 for the x offset, let me go a little bit further away, you can see that in the x-axis, which is the red axis, I don't have any toy randomly placed here to the left of our bounding box, but I have a couple of toys that are placed outside of the border here, because we are only randomizing the position by positive values. If I put minus 50, you can see it starts to randomize in the other direction too, so it exits the room in both ways. And we saw in the previous video how you can limit these toys to be inside the room, so watch the filtering tutorial if you don't know how to do this, but the important part here is to understand that it randomizes the position x and position y values by these two columns. And the same can be done for the rotation. So here you can see that all of our rotation values are 0, so we don't have any rotation of our objects. But if I put a random value for the z rotation, for example, between 0 and 360, now all of my points, and by doing it on the points, it will result on the static meshes that being spawned later. They will have a random rotation between 0 and 360. And one thing to note here is that if you look at the values here, they'll start from minus 180 and they'll go to 180. This is something that you need to get used to with rotations in Unreal. They'll have their value go from minus 180 to 180, and it will repeat itself if you do it multiple times. For example, if I put here a value of 720, you can see again it doesn't have a value that's bigger or smaller than minus 180 and 180. And it's just that it will pick a random value between this, but it will convert it back to a normal rotation, because for rotation you have 360 degrees, and if you map it to minus 180 and plus 180, any value that's bigger or smaller than that, it will just be the same as some other value. For example, there's no difference if I have 360 units of rotation of my objects or 0 rotation, and that's why if I put the rotation to be 360, it will just convert it to 0 because it's the same. And of course, for the scale, you can have the same. So if I put 2, you can see we have a random scale between 1 and 2, and you can see that for each of the axes it's the same scale. This is because we have this uniform scale checkbox marked. If I unmark it, and now you can see that the randomization is happening on each axis independently. So if you don't need to stick to fixed ratio between the sides, for example, here you can see that this car toy is being stretched in one of the directions more than the other, so the wheels don't look like circles anymore. So if you don't need to consider this kind of deformations, for example, if you are doing foliage or something like this where it's not so obvious when you have it scaled by different amounts, you can uncheck this uniform scale, but usually it's a lot more common to use this. And of course, if you don't have uniform scale, you can unlock these fields and change the randomization just for a single axis. For example, right now I am only scaling the z-axis because I have only entered the random values here into the z column. And you can see here into the results of our attributes that our scale in x and y is always 1, and we only have randomization into the scale z value. And understanding how these fields are connected to the actual attributes of the points is very, very important. And I'll show you why right now. So for example, if we want to have this random rotation of our objects, let me go back with the scale of 1 and uniform scale. So we want random position and random rotation of our objects. And it looks cool, but if you look a little bit closer here, where we have these cube toys, they are randomly rotated by their z-axis, so they are not just arranged in a grid, but the problem is that they are always facing with this empty side up, and this is not realistic. If you have randomly scattered some cube toys on the ground, they will most probably not be always facing the same way. So how we can change that? We can try randomizing the rotation with the transform point in some of the other axes. For example, in the x-axis, if I randomize with minus 180 to 180, you can see that I now have all the toys rotated with some random amount. And for example, this cube here is a great example of what we want to achieve. Sometimes this side to be upwards and not just the blank side. But this rotation is just giving some random values of rotation. So you cannot constrain it to be always 90 degrees, which will be laying the cube on some of the sides. And of course, this is causing the other toys also to be rotated, which we don't want. We want them always to stick to the floor with their bottom side. So let's remove this random rotation in the x-axis and let's connect this to our different static mesh spawners. One will be for the toys without the cubes. So in this original static mesh spawner, I have all the cubes here into the beginning. So in this other static mesh spawner, I have deleted the cubes, and into this static mesh spawner, I have left only the cubes. So now I want to split the points. So let's do a random choice. Again, this is shown in the previous videos of filtering the points. So for half of the points, let's unclick fixed and choose 0.5. So half of the points will have a random toy spawned, and the other half will have a random cube spawned. And for our random cubes right now, we want to have a random rotation, which will be always divisible by 90. So how can we do this? So you saw that we cannot control the exact value of the rotation with these transform points. So we needed some other method. And the other method that we can do is, for example, have a random integer value between 1 and 4, for example. And this value we can then multiply by 90. So for example, if we got 1 multiplied by 90 will be 90. If we got 3 multiplied by 90, it will be 270 and so on. So we will get a random value divisible by 90 by having just a random whole number between 1 and 4 and then multiplying this by 90. So how can we do this? So drag out of the discarded pin here. So these are the points that we want to spawn cubes on. And let's do an attribute noise. This attribute noise node will allow you to assign a random value to some of your attributes. For example, we want to set a random rotation role. So here into the input source, let's put $ rotation dot role, and this is how you reference attributes in your fields in your PCG nodes. So first you need the name of your attribute, and then you can specify an exact component of this attribute. Because I can do it for the full rotation value, which will be all the 3 axes, roll, pitch, and yaw. But if I want just one of them, I can put a dot and then write roll. And of course, you can use the interface into Unreal Engine for doing this by clicking here on the plus sign, then choosing the point, and this will list the values that the point has by default. For example, we need now the rotation. Then again, plus sign, and this time instead of choosing the attributes, or how they call properties here, we will add an extractor, and this will be for our rotation. That's why we are choosing this rotator, and here you can find this row. And if I click here, you will see that you will have the rotation.row, or you can type it manually if you are sure that you will not get any mistake, because if you have some spelling mistake, if I put second N here, for example, it will give you an error that there is no such attribute. But if I have it spelled correctly, you will see that we will have as an input this rotation row value. The output currently is set to source, which the source means that it will reference the input. So it's the same as having these fields having the same value. And the mode we have currently, it will be set, which means it will set the random value between this minimum noise and maximum noise value. So if I inspect this attribute noise and look at the rotation row of our object, you'll see that it will assign a random value between 0 and 1, because we have here 0 and 1. If I put 360, it will assign a random value between 0 and 360, like we had with the transform points. So you can manually do a transform points with this attribute noise by referencing the value that you want to randomize. It just does automatically for you. When you put values, for example, here into the last column of the offset, it's the same as doing an attribute noise here with the position.z, because the third column is the z attribute, the z component of the position attribute. So you can do the same with the attribute noise. So now, by having this random rotation, if I connect it here, you can see that it achieves the same result as before by having a random rotation for each of the cubes into the x-axis. But we don't want that. And one thing to know for the attribute noise is that it will create this random value based on the type of the value that you put here into the input source. And because the type of the value currently is rotator value, which can have a decimal part, it will generate a random number with a decimal part. But if I change this input source to the $index, which is an integer value, and I have my noise min to 1 and noise max to 4, you can now see that the values are actually a whole number, which is what integer means. They will not have a decimal part. And if I arrange again by the index, you can see that it has for each point random value between 1 and 4. like I wanted. And now what I want to do is drag out of here, select multiply, and let's connect this multiply here. So what we want to do is multiply this rotation row, and currently you have this input source for the multiply into the A pin set to at last, which means that this is the last attribute that you modified. And if you mark your previous node and look here at the top right of the attributes panel, it will say last attribute rotation row. And if I select here my multiply, this last is referring to this rotation row. And it's the same as putting here $ rotation.row. But the easiest way to chain different nodes together if you are modifying the same attribute is just using this at last. And this at source again means whatever you input here, it will output the result to the same source. So this at last and at source are special attributes that you now understand how they're working. And what you want to multiply here is this rotation row multiplied by 90. So you'll have a random value between 1 and 4, and then you multiply that value by 90. So if I inspect this multiply, you can see now we have all values corresponding to some random rotation with 90 degrees increments. And the current problem is that our cube pivot is not in the center. So our point will be, our cube will be sometimes going into the ground. So let's go into our cubes. Let's drag one of them here. And you can see the pivot point here is at the bottom of the cube. And if we move it to the center, we will no longer have this problem. So let's go to the modeling mode. Let's go to the X form, edit pivot, then click on the center, and then click here, accept. So we now modified this pivot to be in the center for the first cube. Let's do it for the other cubes as well. Edit pivot, center, apply. Then the next edit pivot, center, apply. And edit pivot, center, apply. And the last one, edit pivot, center, and apply. So now all of my cubes have this pivot in their center. And now you can see that all of them are placed on the ground. And they're halfway on the ground because our pivot is in the center. So if we go back to our PCG graph, now we can transform them just a couple of units up. So let's create another transform points, or to apply our knowledge that we can directly modify the attributes. Let's do it another way. Let's use an add node, which all the math functions are the same node, just here the operation in this first dropdown will be different. So here this multiply node and this add node are exactly the same node, but here I have chosen the add instead of the multiply. So now if I drag this the result of this add node here into the static mesh spawner, now into the add node I will not modify the last attribute here, which will be the rotation row. I will modify the position z. So $ position dot z. And what I want to add, I can enter here a value of 10 units. It's too much, so let's do 1. Let's do 2. So 2 seems to be the right value. All of my cubes now are sitting on the ground properly. They have random rotation in the x-axis multiplied by 90 degrees, so they're always sitting on one of their sides. And sometimes you can see they have this letter on the side, sometimes they have the blank side on top. So we have much better randomization of our cubes right now, that we know how we can modify these objects to be placed in our world. And if you remember from the last tutorial, we used a self-pruning node in order to get rid of intersecting toys, like, for example, let's find some here into the level. Let's go back into the selection mode to have the full window. So you can see here that I have some of the toys intersecting with each other. For example, I have two cubes on top of each other. Here I have this snake over this car. And in order to get rid of this, we used the self-pruning node. And the problem right now is that we have two different sets, and the self-pruning is running on a single set. So I can do a self-pruning here, self-pruning node. Let's get rid of this and connect this to a static mesh spawner here. So now I no longer have the snake and the car overlapping each other, but I still have the cubes overlapping each other. So if I do a self-pruning here for the cubes, they are no longer overlapping each other, but I can have now a cube overlapping the other toys, because they are two different self-pruning nodes which are not considering all the points together. So what we can do right now is combine all the points, then do a self-pruning node. But the problem then will be how we can know how to split these points later in order to place different static meshes with each of them. So let's delete these self-pruning nodes. Let's do an attribute here for the first set of points, which will be our random toys, and the second set, which will be our cubes. We will do an attribute again. And let's add, for example, an integer value for each of them. And for the first set, it will be 0, and for the second set, it will be 1. Then we'll merge the points together. And if I inspect these merge points, you can see here at the end, so let's give a name to this attribute. We'll output it to point type, for example, and we'll do the same for the other attribute. And if I inspect this merge point, if I scroll here at the back, we'll have point type 0 and point type 1 based on which of the sets are coming into these merge points. And to have it a little bit more understandable, let's change the type to string from integer, and let this string for the random toys will be random toy, and for the second type, let's do a string and do a random cube. So right now, if I inspect these merge points, I'll have random toy for some of the points and random cube for other points. And right now, I can do this self-pruning. Then I can do an attribute filter. And this attribute filter, let's move everything right now because I have too much nodes here. Okay, so now this attribute filter will check if the last values, which the last modified value is our point type. So if the last value is matching or equal to constant threshold, which this constant threshold will be type string and it will be random toy. So right now, if I inspect this filter attribute elements, all the resulting values inside the filter are having this random toy point type. And if I change to the other output, which is this outside filter output, all of them have this random cube. So if I connect now this inside filter to the first static mesh spawner and the outside filter to the second static mesh spawner, you can see we are now self-pruning all the points, and we no longer have cubes overlapping toys, or toys overlapping each other, or cubes overlapping each other. We have the full self-pruning result for all the points, but we are now spawning two different types of meshes from two different sets, which we achieved by having this attribute having a different value to them. So after we merge them, we have a way to split them again. And if I connect this debug node to the points, you can see, let me find some cube. So here are the cubes. If I enable this and disable this debug, you can see that the bounding box for the cubes, it's much bigger than the actual cube. And this is because when we were sampling our surface, we put a bounding box or extends value, which will fit all the toys. And when we split the toys to two different sets, we can do a much better bounding box for our cubes. It can be smaller bounding box. So let's see how we can edit our bounce min and bounce max values in order to have a much better representation of our shape for the cube. So let's connect this debug here before we add the attributes for our random cube. Let's enable it. And before this, let's connect extends modifier like this. So now let's change the extends modifier value to something that will fit the cube better. So 2, 2, and 2. So you can see now it fits the shape of the cube much better. If I put 4, 4, 4, it's too much, but 2, 2, and 2, it's exactly the shape of this cube. And what this extends modifier will do, let's inspect this extends modifier and look at the bounce min and bounce max values. So it will take this value and it will put a negative representation of this value into the bounce min and a positive into the bounce max. So because I have 2, it will be -2 for the bounce min and 2 will be into the bounce max. And if I do a different value for the z, for example, -5, you can see the bounce min z is -5 and the bounce max z is 5. And this works great for objects that have the same extents vertically, for example. But the other toys that we had here, let's connect them to a debug. And you can see that because their pivot is here at the bottom of the toy, when we put the extends value to a value that will cover the full toy, we'll have this needlessly big extents in the other direction. And you can modify this by a bounce modifier. So instead of the extents, you can modify different bounce with this bounce modifier. So this extents will always change the min and the max value together. But with this bounce here, let's connect it to a debug so you can see the difference. This bounce for the toys we have right now can be changed. For example, with the scale mode, we'll scale the x and y values by 1, which means we'll keep it the same. But the bounce for the z value, so the minimum bounce, we'll scale it to 0. And let me change again back to 1. Let me change to 0.9, 0.8, 0.7. You can see that it's scaling the minimum bounce. So it's taking the value here at the bounce min z and it's multiplying it. Let me inspect this. So this bounce modifier is multiplying this bounce min z by a lower amount each time I change this value. And if I put 0, it will always result to 0, because if you multiply by 0, the result will be 0. So in this way, I'm removing this extra bounce here for our toys that have their pivot at the bottom. But because our cubes have their pivot in the center, I can just use this extends modifier and change their extents to 2, 2, and 2 to closely match the cube. And now if I move a little bit everything here to the right, and if I connect this extends modifier, you can see, let me connect back without this extends. So without the extents, we have less cubes because they are bigger. Their bounds are much bigger. Let me connect. So these are the bounds for our cubes, and especially the ones that are rotated to the side, because we had such a huge vertical bound. They'll take up big amount of space. And that's why if we modify their extents to closely match the shape and we connect it, we now have much more cubes. And because we have a lot more cubes now, we can change this random choice to have more toys instead of cubes, because the cubes are much smaller, so they're much more likely to stay into the level when we do this self-pruning. So let's change this random choice to 0.75. So now we have a little bit more toys, and still we have a good amount of cubes into our level. So this is how you can combine the filtering, which we saw in the last tutorial, with adding attributes, modifying the values of attributes. And this is very, very important to understand how you can add and modify these attributes to achieve the result that you want, how you can inspect the values, how you can use these values then to filter again, like we use this point type attribute. We changed the position, the rotation, the scale, the bounds, so all of the default values that are controlling how the point is placed and where it is placed. We learned how to modify them into different ways. So I took some of the nodes which are most often used when modifying attributes to give you an example. So let's look at which we have already saw and what the others are doing. So this bounce modifier, we saw how to change the bounce with it, and it does have different modes, but by the name of the mode you can understand what it's doing. So the scale will multiply by this in order to scale it. The set will directly give it the value that you put. The translate, for example, it will add this value and so on. So it has different types, but the important thing is that it's changing the bounce min with this first row and bounce max with this second row. The extents is changing together the min and max with it single row, and again you can choose different modes. The transform points changes the position, the rotation and the scale, and it gives a random value between all of them. The add attribute you can use, like you saw here, to add a different attribute to your set. You can output the name of this attribute with this output target. You can change the type and the value that you are assigning with this. So the attribute rename can rename the attribute that you added. For example, this random cube, you can rename to something else with this attribute rename. And this is useful, for example, when you have a couple of different stages of adding detail. For example, first, if you create the building, for example, if you add an attribute that it will say a corner or a wall or something like this, it can be piece type or something like this. But then you can, when working only with corners, you can rename this attribute and assign different values to be a corner type. For example, if you have an inner corner or outer corner and you want to spawn a different mesh for the inner and outer corners or something like this. So this is where attribute rename will work for you. So you will put a name that you want to rename and the new name that you want to assign. So we look at this mathematical operations node as well. So it has a lot of mathematical operations, and for most of them you can understand just by the name what it's doing. So I'll not go through each and one of them, but be sure that you can achieve a lot of different behaviors, and you can do a really complicated math setups that it can give your world very, very detailed filtering or placement of your objects based on a lot of conditions that you chain through different math nodes. So make sure to test a lot of the different options in this marked nodes will give you. And you can use this attribute noise to assign random values. The very important thing is that it will take the type of the input source when it generates the value. So you can use this to your advantage, like we did for our random rotation here. By using the index, we make sure that the value that we have is a whole number. Otherwise, if you don't do it that way, for example, I have it like this, it will generate a random value, which is not a full number, but you can use this mathematical operation and do a round, which will round it again to a whole number. So if I inspect this attribute noise here and check our rotation row, it's just a random number, not a whole number. But if I inspect this after this round operation, it will round it to the closest number possible, which will be a whole number. So this attribute noise and these mathematical operations are very important, and they are often used into complex systems to achieve different results. So the attribute remap is similar to an attribute noise, but it's taking the in range and it's outputting to out range. So if you have in range, for example, from 0 to 1, but you want to have it as a rotation from 0 to 360, you can use this remap. It will take a value of 0.5, for example, if it's between these values, the input range. And if your output range is 0 to 360, a value of 0.5 will be converted to 180, which is half of the way between these values. Let's look at some of the other nodes that I have chosen here. So this attribute partition node we can use instead of this filter. So currently this filter is comparing our point type value to a value of random toy, and it's splitting into two different sets, the one containing random toy and the one that are not. But what if we have more values, so more than two? We will need to create another filter here after the first one to compare the other value. But instead of this, you can do attribute partition. And this attribute partition will look into each of the unique values of this partition that you create. So currently it is the last value, which is our point type. So you can see it splits it into two different sets based on this value. And if I create here an attribute node, and if I create this point type and give it string name of instead of random toy or random cube, I'll put it random object, and I'll connect it to the merge point again. Now this attribute partition will give me three different sets, one with random toy, one with random cube, and one with random object, and it will work for unlimited amount of different values. So if I partition by something else, for example, if I partition by the $ index, it will give me 682 sets of different points, because each point will have a different index. So you can partition by any value by, for example, bounds max, and it will give you two different sets, because for one of them we have bounds set here and for the other we have bounds set here. So we only have two different types of bounds min. So the partition will partition your data based on the differences in the value that you have selected to partition by. And you can have different types. So first you partition by bound max to split this into two sets, and then you partition to point type, and now it will split to three different sets. First will be with the bound max value of 6, 3.5, and 15. The second will have different bound max. The third will have the same bound max, but their point type will be different, because after the partitioning to the bound max, we'll partition then to the point type. So this is how this attribute partition works. And what about this attribute reduce? So this attribute reduce, let's create an attribute reduce with the value of average, for example. Let's choose the position dot x. So if I inspect this, you can see it returns just a single value here. And this is the average position of all my points. So for example, if you want to create some point that's in the middle of all of your different points, so let's create another attribute reduce and do this for the position y. Then let's create a point. We'll create a single point, and if I debug this and create it at local component and change the bounds to something bigger, to -50, -50, -50, then 50, 50, 50. So this is the point I'm creating currently. So it's in the middle of my bounding area. So, but what if I take the average position in x, y, and then z of all my points? So I have the average position in x here, y here, and z here. So now I can use these three values to make vector, and this vector will be vector 3, which will have these three values. And I will use this point that I created, which is currently here. I'll set an attribute, and the attribute that I'll set is the position, and I'll set it to this newly created value here. And let's inspect now this set. I mean, debug it. So let's connect this to the debug node. And you can see now it's in the average position of all my points. So what if I don't want the average? For example, I want the max in x. Let's change this to max. So you can see it moved to the maximum amount what I have into the x direction. For example, for the y direction, I want the minimum, which will be here. So it's in the minimum of my y-axis, maximum of my z-axis, and average in my z-axis. And the important part here is that you can use these nodes in any way with any attribute that you decide. It's not just for position, like for example here, but when you want to replicate some kind of a real world behavior of some placement of your points, you need to think of how you can represent that mathematically, and then you can use these nodes, the mathematical nodes and these reduction nodes, the set nodes, and something like this. So the power that you get from understanding how you can manipulate these attributes is really, really big and really important for creating complex PCG graphs. So the comparison is self-explanatory, you just compare the values. But I want to show you here that some different types of nodes that can generate some data for you, like the random data that we have from the attribute nodes. Here, if I choose to use this density node, for example, this distance node, for example, you can see that here are all the points that I'm generating here. And here is the point that I generated with this reduce nodes. So what if I connect all these points here to the source and this resulting point here to the target? And let's now inspect this distance nodes result. So here at the end, you have this distance attribute, which will give you the distance of each point to this, of each of the source points to this target point that we connected. And we have a value here, which is the distance in world units. So let's use an attribute remap. And what we want to remap is to create a density based on this distance. And the density needs to be between 0 and 1. So we'll have our out range between 0 and 1. And our in range, let's check what it should be. We have the minimum of minus 56 and the maximum of 800. So let's put the in range min to minus 56 and the max to 800. And now let's connect this to the debug points. So I'm debugging with the current density value. So let's copy attribute and we'll copy as the source and target the same points, but we'll copy our distance to our $ density. And after we copy this attribute and we debug to show this attribute, you can see now we have this gradient that the points that are further away from our target point are getting the bigger value and the points that are closer are getting smaller value. So we can use one minus node to flip this, and then we can use multiply node. So let's connect this to the multiply and let's now multiply by 3, for example, and the input will be our density, but the output will be our scale. So now you can see all the points that are lighter are bigger and all the points that are darker are smaller. So based on the distance of our target point, we are creating larger toys, and here at the end they're being smaller. So let's connect this to our static mesh spawner and let's disconnect the debug. So now you can see we are creating bigger toys here, and the further away they get smaller and smaller. So this is how you can use different attributes and multiply them, add them, copy them into each other to achieve the result that you want. So the first thing is to plan what you want to do, and then you need to think about how you can achieve this by using the attributes that you have on your points. So I think this is enough for this video. This should show you how you can use these attributes, and we'll continue with our learning the PCG systems into the next video. If you want to get earlier access to the videos, you can join into the higher levels in the channel. You can subscribe to the channel to get notifications when I release the next tutorial. And guys, I'll see you in the next one. Bye.